In this video, I'm going to discuss how we determine clinical significance when working with data analysis results. So we all know we talk about a lot about statistical significance and making sure that we can make a decision appropriately about rejecting the null hypothesis or not rejecting the null hypothesis. And the p-value associated with that can tell us certain things, but there are also things it can't tell us. So we're going to spend some time talking about some additional measures and different tools we can use to not only think about statistical significance, but also what is the practical significance? How useful is this result given a certain situation? And so the p-value very often is going to give us limited information. So it's going to tell us how likely it is the result we're seeing is due to chance or is due to some explainable cause. But it pretty much stops there. It doesn't necessarily tell us if this result will be useful to us clinically. I mean, we can have situations in which we can find statistical significance, but the difference that's demonstrating this statistical significance might be so small that it doesn't really translate very well to a clinical significance or being something that's clinically useful. So to give you an example, if you were working with a technique to improve someone's range of motion of a joint, and you were able to improve that range of motion by, let's say, 2 degrees, that may be statistically significant, but in a clinical sense, a 2-degree improvement in range of motion of, let's say, the shoulder is not necessarily a clinically important effect. So we might say, well, that's great that it's statistically significant, but does that really mean much to us clinically? And so we need to make sure we're balancing what statistical significance is telling us and then what that might mean to us clinically or in a practical sense. So again, the p-value is not always definitive. It forces us into this dichotomous decision in which we can either say the treatment, was effective or the difference was true or was not true. And we don't always know if the difference we're seeing will translate very well to most situations, and can we generalize that result then to the larger population our sample may have come from. So statistical significance is important in the sense that it helps tell us if this result is due to chance or not, but that's really only half the story. And a good analogy I like to use is if you're trying to determine if there are differences in how something costs, and someone says to you, well, there is a difference in that cost. Well, how much of a difference? And is that difference important to me? If it's a $2 difference in cost, that might not matter. But if it's $1,000 difference in cost, then that's important. So we need to be able to determine what we mean by a difference that is clinically important above and beyond being statistically significant. And so one way to think about this is most of the time when we're talking about experimental research, what we're trying to find out is if one intervention is better than another, or does one intervention work better than not doing anything? Or do 2 interventions, are they the same or are they different? And so we can very often think of this effect or this outcome as demonstrating a trivial difference or trivial benefit. Could it be beneficial or could it be harmful? So when thinking about this in terms of a practical situation, let's say we've got 2 drugs we want to compare on their ability to affect pain. So let's say we're then rating that pain on a 1 to 10 scale. We might find that the 2 drugs show up with different pain scores, but we want to know, is that difference between those 2 pain scores a trivial difference, something that could be explained by chance? Is the difference beneficial? In other words, is one drug doing a much better job of controlling pain than another? Or is the difference we're seeing actually harmful, where one drug might actually make pain worse versus a control or an alternative treatment? So we often think about these effects that we're seeing as being either harmful, trivial, or beneficial. And we want to be able to determine above and beyond the p-value what's really happening in a clinical sense. Are we getting a change that's beneficial, trivial, or harmful? And so what are the ways we can determine this clinical significance and start to make those decisions about whether any difference we're seeing relative to a treatment is going to be useful to us or is going to be beneficial to us in a clinical situation. And so there are several different measures we can utilize. And one of the first and most common is the effect size index. And essentially what this is telling us is what is the magnitude of the difference between groups or the magnitude of the relationship that we might be seeing between two variables. So we usually think of this in terms of group comparisons, but we can use this for correlations. But the magnitude of the difference gives us an indication of how consistent is this difference between scores that we're seeing, and will this difference be consistent and will it likely be present in the population? We might be seeing it in a sample, but is that difference going to be present in the population? So this gives us kind of a basic understanding of the meaningfulness of the effect. So the larger the magnitude of the difference, the more consistent that difference will be from sample to sample, and then more likely the difference that we're seeing in our samples will be present in the population. And so there's some common effect size measures that are out there. There's quite a few, but the most common we're going to see is Cohen's d, which is used for t-testing. We've got partial eta squared, which is used when we're doing ANOVAs. And then we've got the coefficient of determination, or the R squared, that we see when we're doing correlations or regressions. And so the basic understanding is the larger the magnitude, the more likely the effect is meaningful or clinically important. And each of these measures of effect size has its own kind of classifications as to what is small, medium, or large effect. And so we can very often qualify that quantitative value into being a small, medium, or large effect. And it varies from measure to measure. But typically, the larger the effect size value, the more likely the effect is going to be meaningful or have clinical significance. Now, another common way we have of thinking about this are using measures, which should be familiar from your experience with evidence-based practice, the minimal clinically important difference, or the MCID, the minimal detectable change, or the clinically important effect or clinically important difference are common measures we're going to see out there. And so what these are actual values relative to your outcome measure, that within whatever it is you're measuring, if we have a certain amount of change or certain amount of difference using that tool, that would then be considered a difference that would be clinically important. So again, if we're talking about range of motion, we can say, a 10-degree change in range of motion at the shoulder joint will be clinically important. So if we do an intervention that only gets us a 3-degree change in range of motion, that is within that range of 10 degrees of clinically important. So unless we're able to create a 10-degree or more change in range of motion, then a treatment wouldn't be considered to be clinically important, or the difference wouldn't be considered to be clinically important. So that's typically how we utilize these values, and they're all going to be related to whatever it is we're measuring, whatever the outcome measure might be. And each outcome measure that we're working with can have a value for this established. Not all of them do, but some of them do. And so what we're looking for then in using these values is the change we're seeing in our sample, whether it's a pre-post difference or whether it's a difference between a treatment group and a control group, is the amount of change or difference meaningful for that patient? And so using these values, we can make that decision. And so the MCID is typically utilized for patient-centered outcomes or patient-reported outcomes. And that's probably one of the more common applications that we'll see. And very often we can use these values to define quote-unquote success of an intervention. So if an intervention can create a change that exceeds the MCID, then we can say that is a successful treatment, or a treatment that's going to be clinically important to that patient. The clinically important effect is very much like the MCID, except this is usually related to performance type measures. So range of motion, VO2 max, those sorts of things that are more clinician directed outcomes versus a patient reported outcome is typically, we use the term clinically important effect or clinically important difference. And then the minimal detectable change refers to the change that could be occurring that is beyond expected error. So many of the measurements that we utilize have a certain amount of error that we expect to be in place. So again, using the range of motion example, if you're using a goniometer or some other kind of handheld way to measure someone's range of motion, there's a built-in percentage of error. There's human error, there's mechanical error, so we can say that, you know, whatever measure we're getting is probably off by about 3% potentially. 3%, you know, too little range of motion, or 3% too much range of motion compared to the actual. And so the minimal detectable change tells us how much of a change we need to see that would then be considered beyond just error and would likely be due to the intervention that we're doing. So again, let's say we're measuring range of motion and we know the minimal detectable change for range of motion is, let's say, 5 degrees. And so in order to say that the treatment created this change in range of motion, we would need to see a range of motion greater than 5 degrees. Because if it's less than 5 degrees, then it might just be measurement error that makes it look like there's been a positive change or a negative change, depending on the direction of the change or the difference. And so if these values are available to us, we can use these then to look at differences in group means, for example, and be able to say, okay, this difference that we're seeing between the group means exceeds this minimally detectable difference, or the MCID or the CIE, and then be able to say, okay, this change exceeds that value, so it's likely to be not only a statistically significant change, but a clinically important change. Now, it should be pointed out that sometimes we can see differences that are not statistically significant, but might exceed one of these measures. So we might have a situation where the treatment group, their difference compared to the control group exceeds the MCID, but that difference is still not statistically significant. So that can sometimes happen as well. But we can use these again to make a determination. If it's exceeding this value, then it's likely going to be clinically important, and the difference we're seeing is likely to be a clinically important difference. Now, we can also use confidence intervals to determine clinical significance. And as you remember, the confidence interval, typically the 95% confidence interval, is the range of scores in which the true population value likely falls. So if the amount of change we're going to see, let's say, is 5%, and the confidence intervals are, 3% and 7%, then the true population response to a treatment will be somewhere between 3% and 7%. It might not be exactly 5, but it's going to be somewhere between that 3 and 7%. And so we can use these confidence intervals as a way to set up a range of possible responses that could be important or could not be important. And so again, when we're working with a control group, very often we can see the control group change slightly, but how much of that change is just random? And then we can compare the amount of change we're seeing in the treatment group to the amount of potential change we can see in the control group. So that's how we can use confidence intervals to make these sorts of decisions. And so a way to think about this, if we were to graph this out, this 0 here represents the null hypothesis. And very often, this is going to be the mean of the control group. So whatever we're doing to the control group, we're going to measure their response to that. They could be receiving a placebo, they could be receiving nothing, they could be receiving an alternate treatment, but they're going to respond and have a mean in that response. But that is essentially the null hypothesis. And then we're going to compare the mean of the treatment group to that control group mean. So if we want to think about an effect, we would say typically the control group will have a 0 effect. Now, let's say we want whatever outcome measure we're using in order to be a positive influence. Let's say that value has to increase. So let's say again we're talking about range of motion. The control group might have 0 change in range of motion, but for a positive clinical outcome, we want to see an increase in range of motion. And so if the treatment group their mean appears to be trending in the positive direction, then that would indicate that there's a positive effect of that treatment. And then we can see the same thing with negative. Perhaps the treatment group gets worse, and then we can see more of a negative effect. And so we can use the means and confidence intervals of the control group and the mean and confidence intervals of the treatment group to start to make a determination, okay, what could really be happening or probably is happening in the population if we were to do this. So we use a sample and look at their response and then try and make some determinations about what the reality might be in the population. And so what we can do is think about the confidence intervals and the means as creating these boundaries and these areas that indicate beneficial or harmful responses, or in the middle, a trivial response. So again, if this is the mean of the control group, and these dotted lines represent the confidence intervals for the control group, ideally what we'd like to see is the treatment group to be all the way over here somewhere and showing a beneficial response to the treatment, and potentially not overlapping at all with the trivial response that we expect or that we're seeing potentially in the control group. And so what we would do is then use a line. So this line, blue line, represents the middle of it is the mean of the treatment group, and then the ends of it are the confidence interval boundaries for the treatment group. So as we can see here, the mean of the treatment group is somewhere outside of a trivial response. So it's outside, it's different than the mean of the control group, but the confidence intervals tend to overlap the confidence intervals of the control group. So that means that there's a likelihood that in the population, the treatment group would have a very similar response to the control group. And what we see here too is the confidence interval of the treatment group actually overlaps the null hypothesis. So this means, again, as we interpret the confidence intervals, that in the population, the treatment group may actually have the exact same response as the control group. In other words, the treatment had no effect. But even if it had no effect, it would still be trivial. So there's a proportion of likelihood that the treatment will be beneficial. But there's also a proportion of likelihood that the treatment will be trivial and have no effect. So you could argue that it appears that there's a mixed clinical significance here. This is likely statistically significant, but because we have these wide confidence intervals that overlap with the confidence intervals of the control group, that minimizes or reduces the clinical significance of this particular result. Now, we could also have a situation where this blue line might actually go into the harmful area, and that would obviously be concerning for us to say, this treatment might actually make people worse compared to a control group. And so we can see those sorts of interactions. And so this is how we can use the means and the confidence intervals of the control group, and then the mean and the confidence intervals of the treatment group to make a determination of clinical significance. So let's go through an example here. And so let's say we've got this intervention that we've got a group of health sciences students who are learning new clinical skills. And we want to determine the efficacy of using standardized patients on improving student confidence or self-efficacy and their actual skill performance. And so we want to see if using standardized patients compared to a traditional way of teaching these clinical skills will improve their confidence or their self-efficacy in performing these skills and their actual performance. And so we've got 32 people. They do 2 weeks of either traditional types of instruction or traditional instruction enhanced with standardized patients, where we've got people that are pretending to have a certain condition and the students work with them and then practice these skills. So we want to see if that'll have an effect on 2 different measures. The first being self-efficacy, and we're using a standardized measure of self-efficacy that has an MCID of 2.0. And then we're also looking at the skill performance. How many correct things did they do in performing that particular skill? So as we look at the group means here, here's our standardized patient group and here's our traditional group. So we've got 2 groups here that we want to compare on this single outcome. We can see the mean score for the standardized patient group and the traditional group are roughly the same, 2.1 and 2.2. And then here's the standard deviation, 1.5 and 1.2. And then here's our confidence interval range. And as you can see here, the p-value for this comparison, these two groups are compared using an independent t-test. You can see that the p-value for this is 0.54. So if the null hypothesis would be that there will be no difference in score between these two groups, we would essentially have to accept that null hypothesis and say these two groups are essentially not different, and any difference we're seeing is likely due to chance. Okay, now as we look at the skill performance assessment, so the students were assessed on performing all the steps in a particular skill, and they get a point for each step that they performed correctly. And this assessment has a clinically important effect or difference of 20 points, which means if there's a difference in how they perform the skill in one group compared to the other that's more than 20 points, then that's a clinically or practically important difference. So we can see here the standardized patient group had a mean score of 112, plus or minus 38.5. And the traditional group had a mean score of 96 points correct, plus or minus 36.5. And we can see the confidence intervals for each group here as well. Now, this difference was statistically significant. There's a p-value less than 0.05. Again, these were compared using an independent t-test. And the Cohen's d, or effect size, for this particular comparison was 0.44. So these are all values you're going to get in a typical statistical software output. So we can make the determination in this case, for example, that we have statistical significance, and then we also can begin to make some determinations about clinical significance. So let's see how we could interpret these. So let's look at the self-efficacy first. And so what I have labeled here, this is the mean of the control group up here at 2.2, and here is the confidence interval for these two groups. Now, the blue line represents the mean and the confidence interval for the standardized patient group. So as you can see, the middle of this bar would be the mean, and here's the lower and upper boundary of the confidence intervals. As you can see, the confidence interval range overlaps the confidence interval range of the control group. So it's essentially saying in the population, these two groups would be very similar. If this blue line was entirely inside the yellow, then essentially the two groups are exactly the same, and they would likely be exactly the same in the population. There's a little bit of range here in the beneficial area, but it's very small. And as you can see, the confidence interval boundary for the treatment group crosses the null hypothesis. When that's the case, we essentially would be able to say there's really no clinical significance as well as no statistical significance. So now let's look at the skill performance. So as you can see here, here's the mean of the control group for the skill performance, the lower and upper boundary of their confidence interval. And then the blue line again represents the middle of the treatment group and its boundaries as well. So as you can see here, the confidence interval lower boundary for the treatment group crosses the null hypothesis, but there's also a large proportion of it in the beneficial area. Now, this difference was statistically significant, but this limits its clinical significance because the lower boundary does cross the null hypothesis, and there's a proportion where there's a likelihood that the population response would actually be in the trivial area, but there's an almost equal likelihood that the response in the population would actually be beneficial. And so even though the means were different, based upon the confidence interval, we can say that what would be happening in the population is actually a little bit unclear. There's an almost equal likelihood that the response in the population might be trivial or it might be beneficial. It's not harmful, but it's not real clear if this treatment would consistently produce a beneficial response. At this point, we can only say it appears that it could produce a trivial response, which isn't necessarily a bad thing, or it could produce a beneficial response. But it's not a real clear-cut answer. Now, if this blue bar was entirely in the beneficial area, then we could say, you know what, it appears that not only is there statistical significance, because there would be statistical significance if that was the case, but there's also clinical significance because there is no overlap between the confidence intervals of the control group in here in the middle and then the treatment group represented by the blue bar. So ideally, that's what we'd like to see. We'd like to see this blue bar be entirely in the green and indicating that there is no overlap between the confidence intervals. So there is definite clinical significance between these groups, which means the difference is large, the difference is consistent, and the difference will likely be present in the population, which tells us that this is now a clinically important response. Now, the blue line could be entirely in the harmful area, which would be a situation in which we'd say that this is something we don't want to use because it consistently would be harmful or produce a lower score than even a trivial score. So those are ways we could then interpret these confidence intervals relative to the control group. So the conclusions we could make from our example, as I've already alluded to some of them, there was statistical significance found for improving performance using standardized patients. That was not found to be the case for self-efficacy. There was a moderate effect size for skill performance differences. The magnitude was moderate. The confidence intervals for self-efficacy overlap in the mean difference, so the difference of 2.1 and 2.2 was less than the MCID, showing no effect. So let's back up a little bit here. So as we talked about, the MCID for self-efficacy was 2.0. As we look at the difference between these two means, that is less than 2.0. So it does not exceed the MCID. So we could say that this is not a clinically important difference. Now, as we look at the performance assessment, the CIE for this is 20 points. The difference between the two means does not exceed 20 points. That's a 16-point difference, roughly. And so even though this is a statistically significant difference, this difference does not exceed the CIE, which again reinforces this idea that this is probably not a clinically significant result. So let's go back to our conclusions here. So for self-efficacy, the confidence intervals for self-efficacy between the treatment and control group overlap, as I demonstrated with the graph, and the mean difference is less than the MCID. So essentially, there is no statistical significance and there is no clinical significance in the case of self-efficacy. Now, for the performance, the skill performance, the confidence intervals overlap with the null, but there was a portion of that interval that showed a beneficial response. Now, the mean difference did not exceed the CIE. So again, here we have statistical significance, but weak or moderate clinical significance. So clinical significance for, in this situation, would be weak for self-efficacy improvement and possibly beneficial for performance, skill performance, but again, not definitive. So you could then conclude that I could use standardized patients. It's not going to change the student's self-efficacy very much, it doesn't appear, but it may improve performance. But to what degree, I'm not sure. So then you'd have to make a decision, is it worth it to incorporate standardized patients for the benefit, potential benefit that might be there? So that's how we can incorporate some of these different measures of clinical significance in conjunction with statistical significance. So it's important to make sure we're paying attention to those common measures. And so the summary here would be, do not rely exclusively on the p-value to make a decision about the importance of a result. Yes, you can use it to say chance or not chance, but as far as how useful this result would be, the p-value won't tell you that. So that's where we need to rely on some of these other measures. So the magnitude of the effect, is the effect size, will tell us. What do the means of the groups actually tell us? Does one group have a higher mean or a lower mean than the other? And does that mean that, the treatment group has an improved skill performance compared to the control group. We can look at the measures of clinical effect, like the MCID or the MDC. And then what would this mean potentially to the population? Would it mean that the population will likely have a positive response consistently, or is the response unclear? And then consider what that would mean to a clinician. How could they apply this particular result to what they're doing? So hopefully you found this to be a useful primer on how we can use different measures statistically to determine clinical significance in conjunction with statistical significance. And it's good practice to get into using these consistently. Don't just rely on the p-value, but look at other ways you can demonstrate the importance of whatever change or whatever difference you might be seeing.